Hello, and welcome to General Astronomy, Lecture 17, Earth's Atmospheric History and Climate Change. Earth's atmosphere, composed mostly of nitrogen and oxygen, makes our lives possible. It provides our planet with just enough warmth and pressure to enable water to cycle among all three phases, that is, solid ice, liquid water, and gaseous water vapor. It protects us from harmful solar radiation, and it produces the weather patterns that variously bring us days of sunshine, clouds, and rain or snow. In this portion of our lectures, we'll discuss how and why our atmosphere is so hospitable, and how we humans may be altering the very balances upon which we depend for survival. When Earth first formed by accretion of planetesimals, gases were probably trapped within Earth's interior in the same proportions that they were present in the solar nebula. That is, the big cloud of gas that formed our solar system. But since the early Earth was hot enough to be molten throughout its volume, most of these trapped gases were released. Earth's gravity was too weak to prevent hydrogen and helium from escaping into space. The atmosphere that remained still contained substantial amounts of hydrogen, but in the form of relatively massive molecules of water vapor. In addition to releasing water, intense volcanic activity, that is, outgassing, of this early period would have released carbon dioxide and ammonia. Recall that carbon dioxide dissolves in rainwater and in the oceans, where it combined with substances to form a class of minerals called carbonates. For example, limestone and marble are examples of carbonate-bearing rocks. These form sediments on the ocean floor, which are eventually recycled by subduction. At the same time that levels of water and carbon dioxide were decreasing, ultraviolet sunlight broke apart ammonia atoms to create two gases in the atmosphere, hydrogen and nitrogen. The hydrogen, being too light, escaped into space. Through the loss or relocation of water vapor, carbon dioxide, and hydrogen, the remaining nitrogen became the dominant component of the atmosphere. Today, nitrogen still forms the bulk of our atmosphere, about 78%, but it is the other main component that matters the most, oxygen. The appearance of life on Earth set into motion a radical transformation of the atmosphere. Every single cell organism converted energy from sunlight into chemical energy using photosynthesis, a chemical process that consumes carbon dioxide and water to release oxygen. Oxygen molecules are very reactive, so originally most of the oxygen produced by photosynthesis combined with other substances to form minerals called oxides. Eventually, so much oxygen was being produced that it could not all be absorbed to form those oxides, and so oxygen began to accumulate in the atmosphere. Ultraviolet light transforms some of the oxygen molecules into molecules of ozone. The absorption of this energy heats the upper atmosphere, creating the stratosphere and giving protection from harmful UV radiation. About 2 billion years ago, a new type of life evolved to take advantage of this newly abundant oxygen. These new organisms produced energy by consuming oxygen and releasing carbon dioxide. It is a process that's known as respiration, and that's what's used by all modern animals, including humans. The abundance of atmospheric oxygen is due almost exclusively to the presence of life, a situation that has no parallel anywhere else in the solar system. So it's really quite remarkable. I mean, there was pretty much no oxygen in our atmosphere at all until we started getting single-celled organisms that used this photosynthesis to convert some CO2 and water into oxygen. And then, out of nowhere, we suddenly have a massive production of oxygen within our own atmosphere. So, high levels of oxygen are indicative of life. Well, now we can begin to discuss our human influence. So that's the very brief summary of our history of our atmosphere. But now we have to look at what's happening today and what kind of effects it might have in the future. So all life on Earth subsists in what we call the biosphere. It's a relatively thin layer that includes all of the land, the oceans, the crust, even a kilometer down below our feet, and up into the atmosphere about 30 kilometers, reaching into the stratosphere. This is anywhere that microbes have been found. So we call that entire region the biosphere. Well, the biosphere is actually incredibly delicate, even though it's hard to believe because the Earth is so large, relative to us at least. But the biosphere is very delicate, and it's taken billions of years to get to the point where it is today. So, what we're going to do is take a look at how we are affecting this. So, that's why we call this part the human influence. As an example of this sensitivity, consider the El Nino phenomenon, something that happens every few years, in which the temperatures at the surface of the equatorial Pacific Ocean rise by 2 to 3 degrees Celsius. In fact, we just got out of an El Nino, I think, last year or this year. But the point is, this change in temperature can starve out organisms known as phytoplankton, which may have dire consequences. So, for example, during the 1982 to 1983 El Nino, 1/4 of the adult sea lions off the Peruvian coast starved, along with all of their pups. Now, many different factors can change the surface temperature of our planet, so we're going to look into this a bit more. But this is just a really good example to start you off to understand that even 2 to 3 degrees can have such a big consequence, even in the span of a year or two, where 1/4 of all of these sea lions were killed. Well, as you've probably heard, one of the most important factors that affects global temperatures is the abundance of greenhouse gases. So, as we know, that's including carbon dioxide and even water vapor. As we talked about these things with Venus and Mars as being our two closest neighbors that we need to know about. If you're starting this video, I actually recommend going back and looking at the past lectures on our atmospheres and the atmospheres of the other terrestrial worlds, because it's very important to see what happened to them before we talk about our own atmosphere. But anyway, from time to time in our planet's history, natural events have caused dramatic increases in the amount of greenhouse gases in the atmosphere. And records indicated that a change of just a few degrees in the past has led to 95% of all species on Earth becoming extinct. So, again, it's a small number, a few degrees, but it's so important and critical to sustaining life on Earth. Well, we now know that our species is having an increased effect on this biosphere because of our skyrocketing population. Projections now show that there will be more than 8 billion people on Earth in just another 12 years, 13 years, and more than 9 billion by 2050. To meet the demands, we do have to burn fossil fuels, cut down forests, and build giant cities. So it's naive to say that we aren't having some effect, but we're going to just take some time to look through what effect we are having in this lecture. Well, tropical rainforests are vital to our planet's ecology, and they absorb a lot of CO2. I mean, trees take in the CO2 and release their oxygen, so it's very important that we have them. Well, another example of what kind of effect we can have is something called slash and burn. So rainforests occupy only 7% of the world's land, but they are home to at least half of all the world's species on Earth. Nevertheless, of course, we need to meet demands. So we have to make room and cut down lots of these trees and set them on fire. And what I said was slash and burn. It's just a name given to one of these ways that we can harvest. So the rainforests that thrived in Central America, India, and the western coast of Africa are almost gone. We are consuming quite a bit more than can be produced over time, although we have been getting better about these things. So this is an interesting question. So in what two ways does deforestation through this process of slash and burn increase atmospheric carbon dioxide? For this one, you don't really have to pause. We'll just talk about it right away. But there's two reasons. I mean, we already spoke about one, technically. The first would be the fact that we're removing something that uses the process of photosynthesis. So without those trees to remove the CO2 from the atmosphere, it helps to keep it building up in our atmosphere now. But also, the fact that we actually burn a lot of this area, well, burning releases CO2 into the atmosphere as well. So it's kind of a double-edged sword here, where you're getting two bad effects just from this one process. And they contribute together to increase CO2 concentrations in our atmosphere. But as I mentioned, it's not the biggest issue right now. Also, another example of an issue we've had recently, but another one, thankfully, that has been worked on, is the ozone hole. We have banned CFCs, which are chlorofluorocarbons, which are gases that are used in refrigerators and many electronics, and hairsprays and stuff like that. But they were, and still do, destroy the ozone that's in our stratosphere. As we talked about previously, ozone molecules in our stratosphere absorb the UV radiation coming from the sun. So without this ozone layer, solar UV radiation would just make it all the way down to the surface and would be a little bit of an issue. So such radiation actually breaks apart most of the delicate molecules that form living tissue. So a complete loss of the ozone layer could lead to a catastrophic ecological disaster. I mean, our skin would be bombarded by ultraviolet radiation. So again, it's another thing that we introduced into the atmosphere, and we did have a big effect. I mean, there was this ozone hole some years ago. Now, this was discovered first in 1985, and it's an area that's like centered over Antarctica. In fact, you can see that in the images here, where there's at some point a 50% decrease in ozone over Antarctica between 1979 and 2012. The amount at mid-latitudes, where most of us live, it decreased by 10 to 20% in that same period. So as a result, because we're lacking that protective layer, the number of deaths due to skin cancer caused by solar radiation had increased. So it's not great. But like I mentioned, we did ban CFCs, I believe, recently, and the ozone hole is pretty much repaired, as from what I remember. But you can take a look into that more if you'd like. I'm pretty sure it's been recovered, at least. But now we get to the important thing. Now, unfortunately, this has become a politicized topic, especially in today's politics. But I really hope that you can understand through these past lectures and now this one that this is coming from actual data from scientists, and it's very important to discuss. So I won't talk about politics other than mentioning that it is a politicized topic now, but it should never have been that way. This is a very important topic, and we need to trust our studies. So what I'm going to do in this rest of this lecture is just show you some of the data that we've obtained and try to help you see what's actually happening and maybe why a degree or two of temperature increase is a significant deal. So let's jump into this. So I'm going to show you lots of graphs here, but this first one here shows you the carbon dioxide concentrations from 1960 to about 2010. And you can notice that it, in general, increases. And you can actually see the blue squiggle, which shows you the annual cycle. So like every year, there is an up and down variation in the amount of CO2 that's in the atmosphere, which you'll see why in just a moment when I play you a video. But our human effect is really important when it comes to climate change because of our burning of fossil fuels, such as natural gas, petroleum, and coal. We know, which we'll talk about, that this burning does release carbon dioxide into the atmosphere. It is an observed fact. And we now know that CO2 in atmospheres has a profound effect on the greenhouse effect. So just, again, look at Venus and what happened there. I mean, CO2 built up in that atmosphere, and now it's 575 degrees Fahrenheit, I think, on the surface. So it's a bit of a problem. So this is a good graph to show you, in the past 50 years, what's been happening to our CO2 concentration in the atmosphere. But I know this alone doesn't really tell you much. Plus, it's not a whole story. It's only 50 years. So what we'll do is we'll back it up even further. Let's go back 1,000 years into our past. There has been some natural variations in this concentration, of course. Things on Earth, or in the universe in general, do tend to fluctuate. But the value has skyrocketed since the beginning of the Industrial Revolution in around the year 1800. If there are no changes in our energy consumption habits, by 2050, the CO2 concentration will be greater than 600 parts per million, which, if you look at this graph, isn't even close to the top of this graph. I mean, it would be off the screen. So this shows you CO2 concentration for the past 1,000 years, and notice once the Industrial Revolution starts, well then, boom, it just takes off. And then it tries to show you the temperature here as well, and how closely it may correlate. Now, a lot of people say, correlation doesn't mean causation, but we'll show you something soon that can help you realize that it's not natural factors that are causing this increased temperature, and especially at this rate. So, okay, again, I know some people will say, well, okay, that's only 1,000 years. The Earth has been here for, 1,000,000 years. Oh, more than that, but it's just a random number. So we can actually use models and go back even farther. Now people say like, oh, there's ice ages and natural fluctuations. You're absolutely correct. Here is a chart showing a simulation from models that went back, 650,000 years. In the last 650,000 years, CO2 levels have never been above 300 parts per million. But if you look here, well, here's 1950, it went over the 300 part per million, and it's already at something like 400. I don't know when this chart was made, I forget, but the point is, it's not great. And notice, yes, there are these fluctuations naturally, but then look at what happens in the last, 100, 200 years. It's actually really quite terrifying. So I know graphs don't always tell a whole story for some people, so we'll get into some more things here in just a moment. So I showed you a couple graphs just showing CO2 concentrations in the atmosphere. So it is of concern because we know that this strengthens the greenhouse effect and raises Earth's average surface temperature. Right? We talked about this on Venus and Mercury. Even in our general discussion of atmospheres, we studied the greenhouse effect, how it acts effectively as a blanket on our planet. So the recent dramatic increase in atmospheric CO2 has produced an equally dramatic increase in average surface temperature, and this is what we call global warming. Now, some people are a little confused because we use the term global warming and we talk about climate change. The two don't exactly mean the same thing. Global warming is a consequence of the changing climate. So it's not like we just suddenly changed from saying global warming to saying climate change. They go hand in hand. But climate change is a little bit more all-encompassing for the most part. So the effect of global warming can be seen around the world already. Glaciers are receding across the entire planet. Sea ice is being reduced. In fact, around the North Pole, it's been reduced by about 20% in the last, 35 years or so. And a portion of the Arctic ice shelf has broken off, and we're about to lose another very large piece of it. So we can see that this is becoming an issue already. So what I'm going to do is play you this video. I'm going to have a little copyright claim on this, but it's really important, so I'm going to keep it in my lecture. This is a video showing you the CO2 concentrations in the atmosphere over the course of 1 year. And it shows you how important the seasons are and vegetation is to this CO2 production and consumption. And notice where the CO2 is coming from. It's coming from our industrialized worlds. So this is just a minute or two, so we'll let this play out. And there's a guy that talks about this as it goes on. So,
hi, this is Bill Putman. I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking at is a supercomputer model of carbon dioxide levels in the Earth's atmosphere. The visualization compresses 1 year of data into a few minutes. Carbon dioxide is the most important greenhouse gas affected by human activity. About half of the carbon dioxide emitted from fossil fuel combustion remains in the atmosphere, while the other half is absorbed by natural land and ocean reservoirs. In the Northern Hemisphere, we see the highest concentrations are focused around major emission sources over North America, Europe, and Asia. Notice how the gas doesn't stay in one place. The dispersion of carbon dioxide is controlled by the large-scale weather patterns within the global circulation. During spring and summer in the Northern Hemisphere, plants absorb a substantial amount of carbon dioxide through photosynthesis, thus removing some of the gas from the atmosphere. We see this change in the model as the red and purple colors start to fade. Meanwhile, in the Southern Hemisphere, we see the release of another pollutant, carbon monoxide. This is a gas that's both harmful to the environment and to humans. During the summer months, plumes of carbon monoxide stream from fires in Africa, South America, and Australia, contributing to high concentrations in the atmosphere. Notice how these emissions are also transported by winds to other parts of the world. As summer transitions to fall and plant photosynthesis decreases, carbon dioxide begins to accumulate in the atmosphere. Although this change is expected, we're seeing higher concentrations of carbon dioxide accumulate in the atmosphere each year. This is contributing to the long-term trend of rising global temperatures. The Orbiting Carbon Observatory 2, or OCO2, will be the first NASA satellite mission to provide a global view of carbon dioxide. OCO2 observations and atmospheric models like GEOS 5 will work closely together to better understand both human emissions and natural fluxes of carbon dioxide. This will help guide climate models toward more reliable predictions of future conditions across the globe.
All right. So that's an excellent video showing you our CO2 production and how important vegetation really is. So I figured I'd keep that one in my lecture despite a copyright claim coming through, I'm sure. But we'll see. Now that we have this discussion of CO2 concentrations leading to rises in temperature, let's look at temperatures. Since the Industrial Revolution in the 1800s, here's the average yearly temperature, or difference from the average temperature each year. Notice how quickly it's rising. Okay, so this is incredibly important. So we saw CO2 levels rising. Well, now we see our temperatures rising significantly. And again, it seems like a small number, but we already saw, just as that one example, 2 to 3 degrees killed off in a span of a year a quarter of all sea lions in an area because of that. So let's dive into these numbers some more. Here shows monthly temperature anomalies from 2007 to 2016. The orange bars indicate months that set a new temperature record at the time that they occurred. And for example, in the past 3 years, that is in this region here, 24 months set an all-time record for warmth. In some cases, monthly records that were set in 2014 were broken in 2015 and in 2016 again. So it's a huge deal. Just in these last, say, 10 years, temperatures on average have been anywhere from 1 to 2 degrees above normal. And we are constantly breaking records. And that's very problematic. So here, I don't know if I have this. Let me click on this. There we go. That's what I'm looking for. So here, I want you to see this. So this shows you the time series from 1884, about when the Industrial Revolution began, to 2016, what the average temperature looks like. So this is a quick visualization of this. So take a look at this as time progresses through the years. So it shows you temperature differences, and it shows a little bar on the bottom. So blue indicates cooler than average, and then the yellows and oranges indicate a warmer than average region. And you don't see much of a change for a little while, but it becomes very apparent soon. So I'll just let this run for a few minutes. And you can see that it fluctuates, right? It's not always warmer in one area. It could get cooler for some years and then warmer than average. But as it goes on and we get closer to 2016, we start to see a very global pattern where almost everything ends up in the oranges. And in fact, some places get to the bright reds. All right, so we're at 1980. We see a lot more orange than we did at any point before. 1991, when I was born, it's getting a lot more red. And now it gets kind of scary. So globally, we see increased temperatures. To the point where it becomes, like I mentioned, kind of scary. So this gives you an idea of what's actually going on. And this is direct data from spacecraft orbiting the Earth and taking data through the years. By the way, 2016, last year, was the hottest year ever on record. This one only shows from January to September, but the trend continues. But this shows you warmer than average pretty much across the whole planet. And in many areas where there's dark red, that is the record warmest it's ever been in those regions. So 2016 was the hottest year that we have ever recorded. So take a look at this. This shows a nice graphic of temperature changes through the years, again, starting from about the Industrial Revolution. So this is showing temperature increases. So as it moves away from the center, temperature is increasing. And here's the 1.5 degree mark and then the 2 degree mark. Those are the two marks that are important to us today. Because if we pass 2 degrees, there's kind of a no going back sort of thing. And 1.5 is about what we're passing already. So this is a big deal. So I'm going to let this run one more time so you can see this. It's a very nice way of putting this data into a visual layout. And notice that in the last couple of years how quickly it expands. It's not great. So, temperatures are important, right? And again, I've mentioned that yes, you can go back and see natural variations in temperature. So let's do that for a second. This is a wonderful graphic, a really, really good one. And I don't have the time to go through this whole thing and read everything for you, but what I will do with any of these things that I've been clicking on, they will all be posted in the description of this video so you can explore them yourself as well, perhaps in a bit more detail. So I'm going to have to scroll through this pretty quick, but this is the timeline of Earth's average temperature since the last ice age. Now, I'm just going to read what it says. So when people say the climate has changed before, these are the kinds of changes they're talking about. So here's a plot of temperature, right? Here's the average, 0 degrees. And then anything to the right of that is warmer than average. Anything below is cooler than average. So I'm just going to quickly scroll through this again. I'm not going to really read much of it, but you'll start to see what's going on here. So this is starting 20,000 years BC, all right? So temperature starts out very cool compared to what it is on average throughout all this time period. There are fluctuations, and yes, it does absolutely warm up. In fact, well, let's just keep going. So yes, it's warmer. Temperatures reach modern levels back 9,000 years before. But, you know, it's just, there are these natural variations. And nobody discredits this. We know this is true. So technically, anybody that says this has always happened is correct. But they're incorrect in thinking that what's happening today is the same. So that's what we'll see very soon. So here, I don't want to go all the way down, but here we're just crossing into the recent years. So here's 1600s, 1700s, and here's the 1800s. So this is when the Industrial Revolution begins. So we've gone through many, many years, and the variations have been very slow. While they do exist, they've been very slow. But look at what happens in the last 200 years. This is the problem that we're talking about. This is the human-induced part of things that worries everybody. So there have been these variations, but look at how significant this is now. So we're at the present day, well, 2016, so last year was right here. If we don't do anything and we keep doing what we're doing today without many more regulations, we will skyrocket by 2100 up to several degrees above average. Being optimistic, we might only go, maybe 2 degrees above. And the best case scenario, that's if we do if we immediately do some significant adjustments to what we're doing, we might stop at about 1 to 1.5 degrees in increase. But it's not great. I mean, being optimistic, we're talking 2 degrees, which is already very bad. So this is why it's so important, and things like that climate accord that we were a part of, or well, we still technically are, is so important. While it still barely scratches the surface, it's a good start to get every nation in the world together and work on something that's this important. So from here, what I'm going to do is show you this from Bloomberg. Now, this is incredibly important. And again, I'm going to link this. I recommend you going through it yourself. But let's take a look at this. So I'm going to read what it says here. Skeptics of man-made climate change offer various natural causes to explain why the Earth has warmed 1.5 degrees Fahrenheit since 1880. But can these account for the planet's rising temperatures? What we're going to do is go through these and figure out how this is working. And this is all from NASA's Goddard Institute for Space Studies. So here's again a plot of temperature increases in the last roughly 200 years. So let's take a look. People say that Earth's orbit changes. Maybe we get closer to the sun or whatever, and we wobble on our axis. So, is it Earth's orbit that is causing our increase in temperature? Well, take a look at this. Based on orbital changes alone, there's no correlation whatsoever. So this band shows where temperatures fall in 95% of climate simulations. This is 95% confidence here, so this is a big deal. It almost certainly has nothing to do with orbital changes. Okay? Well, what about the sun? The sun's temperature does vary over decades and centuries, and people like to believe that the sun's slight increase in energy output over the years is causing this increased temperature. It's not a bad thought, but as you can see again, with 95% confidence, it's not even close. So it's not the orbit or the sun's change in temperature itself. What else? What about volcanoes? Volcanoes certainly do lead to a warming of the Earth. Human industries emit about 100 times more CO2 than any volcanic activity, and eruptions release sulfate chemicals that can actually cool the atmosphere for a year or two. So, although it does fluctuate a bit more than the other ones we've seen, again, 95% confidence, it has nothing to do with it. So this is not the answer either. And I've actually seen recently some things going around the web, primarily on Facebook, with a meme showing a volcano releasing, gas and stuff, but it mentioned that it outputs way more CO2 than humans would ever, and it's simply false. I mean, you can actually look up the numbers on what the average output is for volcanoes and what our human average output is as well. So volcanic activity is not doing this either. So is it all of those natural factors combined? People like to think that it's natural factors that contribute to this, and again, I mean, there's hardly any correlation. Overall, there's dips and increases, but it's pretty much right along the average. So natural factors are not causing this. What about deforestation? Right, we talked about this a little bit. Humans have cut, plowed, and paved more than half of the Earth's land surface. Dark forests are yielding to lighter patches, which reflects more sunlight. So actually, in a sense, it's overall cooling the planet a little bit, because we are now reflecting a lot more light because the albedo is increasing. So that's not it. What about ozone pollution? Another thing that we talked about with CFCs. Well, not really. The overall effect is, well, nothing really. There might be a slight increase because of it, but we've also, again, banned CFCs, so there's really no effect overall. And again, aerosols. Well, some pollutants do cool the atmosphere, and the sulfates that are in aerosols from coal burning and things like that, these aerosols can actually offset some of the warning, but they also cause rain to become more acidic. But again, the point is that it doesn't have an effect. So here is our answer. Greenhouse gases. Atmospheric CO2 levels are 40% higher than they were in 1750. This green line shows the influence of greenhouse gas emissions. There's no contest. So see for yourself. Let's put all of these human factors together and look at that correlation with 95% confidence again. Overall, there is a very significant match here. So now the last one, put everything together, all factors, both human and natural, and look at the correlation. So this is very, very important, and this is all from NASA's work. So if you want to reference this, I'll have it in the description, but I think it's very important, and this is one of the most useful graphs I think I've ever used when discussing climate change, at least. So let us continue now, just a little bit further. So we're going to summarize now. The case linking global warming with human activity rests on three basic facts. First, the greenhouse effect is a simple and very well understood scientific model. We can be confident in our understanding of it because it is so successful in explaining the observed temperatures of the other planets, right? Look at Venus and Mars again, for example. Given this model, there is no doubt that a rising concentration of greenhouse gases would make our planet warm up more than it would otherwise. The only debate is how soon and how much. 2. The burning of fossil fuels and other human activities are very clearly increasing the amounts of those greenhouse gases in our atmosphere. Observations show that currently the atmospheric concentration of CO2 is significantly higher, about 30 to 40%, than it has been at any time during the past million years, and it is rising rapidly. We can be confident that the rise is a result of human activity because the atmosphere is becoming enriched in molecules of CO2, carrying a distinct ratio of isotopes that's present in our fossil fuels. And 3. Climate models that ignore human activity fail to match the observed rise in temperatures, like I just showed you in that model from Bloomberg. In contrast, climate models that include enhanced greenhouse effect from human production of greenhouse gases match the observed temperature trend quite well, again, as we just saw. Comparisons between observations and models therefore clearly indicate that global warming results from human activity. Now let's take a look at what happens in a worst-case scenario model. So you kind of saw it in that really big graphic that I showed you, but here's another one of those graphs, and this is going to go all the way to the year 2100. So this is a simulated global temperature. If we continue doing what we're doing today, this is what our temperature increase might look like. It is devastating. 2 to 3 degrees is already enough to pretty much ruin everything. But if we don't change anything by the year 2100, we're talking 5 to 6 degrees above average, and that, you can't recover from that. So our children and grandchildren are going to be living in the warmest climate that any generation has ever experienced, and it's not great. So this is, I'll admit, a worst case scenario, but we have to know what can happen so that we can discuss what to do about it. So let's just talk about some very quick consequences. I'm just going to read through these. So polar regions will warm the most, causing ice to melt. This is clearly threatening to the species of the region, such as polar bears, which depend on the abundance of ice flows and are already endangered. But it also warms the oceans elsewhere and changes their salt content as melting ice pours more fresh water into the sea. The influx of large quantities of fresh water into the oceans may alter ocean currents, such as the Gulf Stream within the ocean that regulates the climate of Western Europe and parts of the United States. So it's something that not many people really know about, but if we don't have ocean currents, our climate will change drastically. So that is one significant effect of this, fresh water leaking into our salt oceans. Furthermore, melting polar ice may significantly increase sea levels in the future, but global warming has already caused a rise in sea level for a different reason. Water expands very slightly as it warms, so slightly that we don't notice the change in a glass of water, but enough that the sea level has risen some 20 centimeters in the past 100 years. This effect alone is likely to cause the sea level to rise another 30 centimeters during this century, with potentially devastating effects on the coastline. So even without the melting of the ice, just because it's getting warmer, water is expanding, and so our coastlines are being reduced just from the slight expansion of water. Depending on how long it takes to stabilize greenhouse gases, the expansion could raise sea levels another 3 meters in subsequent centuries. The added effect of melting ice could increase the sea levels much more. Furthermore, the famous glaciers of Mount Kilimanjaro are rapidly retreating and may be completely gone within another decade. More ominously, recent data suggests that the Greenland ice sheet is melting much more rapidly than models have predicted as well. If this trend continues, sea levels could rise as much as several meters, enough to flood most of Florida by the end of this century. The fact that the waters of the Gulf of Mexico are the warmest level in at least a century may be contributing to the greater strength of hurricanes that have recently blown through the Caribbean. Generally speaking, the greater overall warmth of the atmosphere will increase evaporation rates from the oceans, which leads to more numerous and more intense storms. Ironically, this fact means that global warming can lead to more severe winter blizzards. So there's that famous politician, I forget his name, who came into I think it was the Senate floor with a snowball to counteract global warming. But remember, it's global warming, but the climate is changing in a way that things are becoming more extreme. You have to think of extremes, not just the warming. And that's part of why we moved away from saying global warming, because it makes people think, like, if it's snowing out, then global warming can't be possible. So just think of extremes. That's why we discuss it like this. We could get more severe blizzards, a lot more tornadoes, bigger hurricanes, longer hurricanes, things like that. And in some regions, spring is even arriving earlier, which can lead to drier summers and greater wildfire risks, something that is very apparent, especially even out in the west right now of the United States. At the time of this video, they're just coming out of one of the worst heat waves we've seen in a long time, where temperatures were steadily, I think, over 120 degrees in some areas for a couple days. So it's a big deal. And we have to be very careful with what happens from here. So I hope you took something very important away from this lecture. There's so much I could talk about, but I don't want to go too in depth and lose you too much. So again, I hope you learned something from this. And yeah, if you have questions, let me know. Those resources will be in the description if you want to take a look at them. Yeah, so thanks for watching. Have a good day, and I'll see you in the next video where we start to transition into topics preparing us to discuss stars. So we'll talk about light and how light works, since that's what we see from stars. And then we'll talk about the nature of stars in general before we go into the gutty details. So I'll see you in that video. Take care.